Here's the next example in section 2.2. Let f of x equals to x squared minus 4x plus 6. Find the critical value of f. Remember, the critical value is a turning point. This is where f prime of x equals to 0 or f prime of x is undefined. Okay, that's our critical value. So for that, we need the first derivative. So f prime of x is going to be 2x minus 4. This can't be undefined since we don't have a variable that we're dividing by, but we can set it equal to 0. And if we do, we add 4 divided by 2. So our critical value is x equals 2. So this is a turning point. Then we want to find f double prime of x. So if f prime of x equals 2x minus 4, then f double prime of x is going to be the derivative of this, which is simply going to be 2. Part C. In order to determine whether the critical value is a relative maximum or relative minimum, find f prime of 2 and determine concavity at the critical value. So this is a constant function. So no matter what my input is, my output will always be 2. So f double prime of 2, and again, the input could be anything, will always be 2. Now, what do we know about concavity? If the second derivative is positive, then this is going to be concave up. And if the second derivative is negative, this is going to be concave down. Concave up will be a U shape, concave down will be M shape or part of an M shape. Okay, so this is the second derivative is positive, which means our graph is going to be concave up. So if our graph is concave up, then the critical value, which is the with the turning point, this is going to be a local minimum. This is a local minimum since concave up, which means it's going to be U-shape. Based on concavity determined in part C, is a critical value local maximum or local minimum, a relative minimum, relative, local, same. So in this case, it's going to be a relative minimum. So if it's concave up, we always get a relative minimum. If it's concave down, then we always get a relative maximum. And if you graph this, the graph of this function looks like this. This is going to be, your x equals to your critical value, and we can see that it's a local minimum since the graph opens up. Another theorem, let's find the points of inflection. Remember the point of inflection from like way back here, it's when concavity changes from concave up to concave down. And before we were approximating, now we're going to have a mathematical way of finding the inflection points. So a function has a point of inflection, then it's going to be when the second derivative is 0 or the second derivative does not exist. So here's a quick summary. What does a first derivative of f prime tell us? It tells us if a function is increasing or decreasing, and it tells us that if the first derivative is equal to 0, then we have a relative maximum or a relative minimum, which basically is a turning point. Second derivative says if the second derivative is greater than 0, then it's concave up. Less than 0, it's concave down. And if we have a critical value, then a concave up, which means it's going to be U-shaped, that critical value will be a local minimum. If it's concave down, which will be an M shape, that's going to be a local maximum. And then when the second derivative is equal to 0 or doesn't exist, then that's a point of inflection. If you forget what's what, because there's a lot of information to remember, you can just refer back to the summary page. Here's an example. Given f of x equals to x cubed minus 6x squared minus 3x plus 1, find the point or points of inflection and verify this using Desmos. So what do we need for points of inflection? Points of inflection occur when the second derivative is either 0 or when the second derivative is undefined. This gives us the points of inflection. So first, let's find the first derivative. This is equal to 3x squared. 2 times 6 is 12 minus 12x minus 3. The second derivative, 2 times 3 is 6x. This is going to be negative 12. This can't be undefined because we don't have a variable on the denominator, but we can set this equal to 0. So if we set this equal to 0, you add 12 divided by 6, you get x equals 2. X equals 2 will be a point of inflection. Let's verify this by graphing it on Desmos. Okay, so our function is as follows. Our function is f of x equals to x to the third power minus 6x to the second power minus 3x plus 1. All right, now let's examine the function. So the function, this is an M shape, so it's concave down, concave down, concave down. Okay, it's going to be concave down. It's going to keep going, and then at this point right there, which is the point. If I get it exact, it'll be, it'll be x equals to 2. At that point, I can't get it exact, but you guys get the idea. At x equals to 2, this is going to change from going. So look, like you can see it, right? It's going from an M shape to a U shape. So exactly at that point, if I could get it, that's going to be our point of inflection. Next example. Consider the function f of x equals to 7x plus 7x to the negative first. Now, where's the function undefined? Not the first derivative, not the second derivative. So if I just rewrite this as f of x equals to 7x plus 7 over x, the function is undefined if the denominator is 0. So when x equals to 0, f of x is undefined, since we cannot divide by 0. Okay, we have a function undefined. Next, what are the critical numbers? Critical numbers occur when the first derivative is equal to 0 or when the first derivative is undefined. So what we need for this is we need the first derivative. So we're going to say that f prime of x is equal to 7. Negative 1 times 7 is negative 7, and then the exponent decreases, so that'll be negative 2. I'm going to rewrite this as f prime of x equals to 7 minus 7 over x squared. So when this is equal to 0 or when it's undefined, the first derivative, then we have the critical number. So let's think about when is it undefined. This is so if you divide by 0, it's undefined. So if x was equal to 0, then the function is going to be undefined. So x equals to 0, this is a critical number. We also have a critical number when this first derivative, which is 7 minus 7 over x squared, is equal to 0. We're going to clear the fraction as we did before. So to clear the fraction, we are going to multiply each term by the least common denominator, which is x squared. So the 7 gets multiplied by x squared, this gets multiplied by x squared, this gets multiplied by x squared. So the x squared over x squared, this cancels. That's the whole point of clearing the fraction. And look at what we have left over. We have 7x squared minus 7 is equal to 0. We move the 7 to the right, so we get 7x squared equals to 7, x squared equals to 1, so x is going to be plus or minus 1. So our critical numbers are going to be 0, negative 1, and positive 1. C. Find the interval or intervals where f is increasing and decreasing. So increasing, decreasing, this comes from the first derivative test. So I'm going to make an interval. I have negative 1, I have 0, and I have 1. So I'm going to create these separate intervals. I'm going to label the intervals first. So the first interval is from negative infinity to negative 1. The second interval is from negative 1 to 0. The third interval is from 0 to 1. The last interval is from 1 to infinity. Okay, these are my 4 intervals. I need a test point. So here, I can just pick x equals to negative 2. In between 0 and -1, I can pick x equals to -0.5. In between 0 and 1, I can pick x equals to positive 0.5. And to the right of 1, I can pick x equals 2. Those are our test points. Now, the first derivative test will tell us if the function is increasing or decreasing in each interval. So now we're going to take the first derivative at each of these points. So we want f prime of -2. We want f prime of -0.5. We want f prime of positive 0.5. And we want f prime of 2. We don't really care about the answer. We just care if it's positive or negative. So once again, do not do this by hand. Put this into Desmos. Just put in the function, your first derivative function, which is this one, 7 minus 7x squared, and then find f prime of -2, etc., etc. So f prime of -2, this comes out to be 5.25. This is positive. F prime of -0.5, this comes out to be -21. So the first derivative is negative. I'm sorry, both of these are going to be -21, so they're both going to be negatives. And then here, f prime of 2 is going to be 5.25, which is going to be positive. Okay, so it's positive. So remember, and I'm gonna keep drawing this out because I really want you guys to understand what's going on, not just memorize it. The first derivative is the slope of the tangent line. The slope of the tangent line is positive, then the function is increasing. Slope of the tangent line is negative, that means the function is decreasing. Negative, function is decreasing. Slope of the tangent line is positive, so the function is increasing. Okay, so we have our intervals of decreasing, our intervals of increasing. I'm not going to write those in interval notation. We've done that in a previous example, but these two, you would put a union. These are increasing. These two put a union. These are decreasing. Next part, find the interval or intervals where it's concave up and concave down. So first, let's list the first derivative. Our first derivative, f prime of x. This is equal to 7 minus 7x to the -2nd power. Now, if I want to take the second derivative of this, then this is going to be derivative of this is going to be 0. It's a constant. -2 times -7 is 14. We subtract 1 from the exponent, so it's 14x to the -3rd. And so f double prime of x is going to be 14 over x cubed. Now we have a point of inflection, or sorry, concave up and concave down. For that, we need to find a point of inflection, because a point of inflection where it goes from being concave up to concave down. So point of inflection happens when f double prime of x equals to 0, or when f double prime of x is undefined. So this is going to be undefined when x equals to 0. Now if I take 14 over x cubed, set it equal to 0, I would multiply both sides by x cubed, and this will give us 14 equals 0, which can't happen. So there's only one point of inflection, which is x equals to 0, which I'm going to put in the middle. So the interval here is from -infinity to 0. This is from 0 to infinity. And take a test point. Take x equals -1, take x equals +1. I take this test point, and now to determine concavity, I need to determine what f double prime of x is. Not f. The first derivative is only for increasing, decreasing. For concavity, we need to have f double prime. So f double prime of -1 is -14, and then f double prime of 1 is +14. So in this interval, this is going to be, since the f double prime is negative, this is going to be concave down, and then this will be concave up. So we're going to get an M shape over here. We're going to get a U shape over here. And verify using Desmos. Please do it yourselves, and we will also do this in class.